Hey, what's up, everybody? It is Thursday. Oh my gosh, it is Thursday. It's Hassan Friday. I didn't even say that once today yet. I can't believe it's Thursday. It's just the deck. It's just crazy. It's just everything flies by. It just seems. I can't even believe it. We're like over. Are we halfway done with the semester? We're pretty far into the semester right now. So if you're here, say hey. We just started office hours. It is for some reason cold in Texas today. How is it cold? Like last night, it was like freezing. What temperature is it? I'm just shocked by the temperature. It's my random thoughts of the day. It says it's 62 degrees. Oh my gosh, and the low is 44 today? What? Craziness. No wonder last night it was probably pretty cold. Yeah, that's pretty crazy. AccuWeather forecast right here. Wish I could look at like last night's. I do not even know how it got so cold last night. Wind gusts up to 32 miles per hour. Yes, we were hearing that wind. So a bit of craziness there. Just who'd have thought? In March, getting down to the 40s. That's insanity. Of course, we had the crazy weather earlier in February. The absolute insane weather. No power, all that stuff. So let's hop over. Let's start doing some really tough 201 assignments. Let's do some probability stuff. We'll see who jumps in. Feel free to jump into the office hours now. I'm pulling up some 201 as we talk in the background right here. And we're probably going to do some probability if we don't have questions. We can add it to the video here. So if you join at any time, feel free to say, hey, I've got the probability stuff up. Let's do it. We did question 1 earlier today, so let's hop to question 2. Let's do this. Let's do some probability questions here for 201. Let's do this. Okay, so here we are with some probability 201 stuff. We've got right here. It's 158. I guess I did start early. It's like, wait a minute. We are streaming right now, right? It'd be so funny if I streamed a full office hours and I just like was not here, like I was not broadcasting, and then at the end I was like, no one talked. Oh, because I wasn't streaming on the internet. So it wouldn't be really funny. I'd just be like, I was gotta make sure I'm streaming. Suppose that 51% of families living in a certain country own a laptop and 20% own a tablet. The addition rule might suggest that 72% of families own either a laptop or a tablet. And so this is when we do the addition rule right here. We would add together the probabilities, but you'll notice that these probabilities here are not disjoint of each other. So when we add together things, and this is a good note to have right here, we've got some kind of cheat sheet notes right here that I've created for us, that when we add together events, we need to have them be disjoint. So if you don't have this table written down, it's a very good table to have written down, that when you multiply, you're going to say and then they need to be independent. If you're adding, you use the word or, they need to be disjoint. Same thing works for subtracting, which is the complement, and complements are disjoint. Just by virtue of you subtracting, they are complements and they are disjoint. So I really think that table can help. So what's wrong with this problem right here is that these are not disjoint events. A family may own both a laptop and a tablet. The events are not disjoint. The addition rule does not apply. So 100% right there. So we can't add these together and get the probability of owning a laptop and a tablet. Just think about this. What is the probability someone owns a laptop or a tablet or a smartphone? Well, you can own multiple things. So you can't say the probability of owning a laptop is 70%, the probability of owning a smartphone is 50%, because automatically you go over 100%. And as we saw from the first problem earlier today, probabilities must be, if you look at all the probabilities, must add up to 1. You can't get over 100% probability. So, a simpler question, but does the addition rule make sure that we know that when we add together events, they need to be disjoint. So the rule there is disjoint. The next problem right here. Ooh, this is a good one. For each of the following, list the sample space. So the sample space is everything that could occur. When you think about sample spaces here, we've got some really great graphics right here showing us the sample space of when we sample coins and we do 4 coin flips. So you can see you could get all tails, you could get all heads. And so we're going to do the same thing for this problem. We're going to list all the sample spaces. And I might even use a new slide right here and draw it out on these slides. Okay, because I got a lot of things open. This will probably be easier to find. So let's go right here. Which of the following is the sample space for the order of heads or tails when you flip 2 coins? So you're going to flip 2 coins right here, and we need to think about the sample space of 2 coins. So with flipping 2 coins, you're either going to have heads, so we'll do it as this. So this is heads. You could have tails, or you could have the following. Sorry, my T's. The color will hopefully help, because my H's are going to be clear to read, and my T's are not. So you could get heads, tails, heads, or tails. Now, this one's interesting because the probabilities right here are going to be 0.5 times 0.5 for all of these. Every single one of these has a probability of 25% because they're all equally likely, and we can show it mathematically. Heads and tails is 50-50 right there. So this is the set of all outcomes right here, and they are all equally likely, yes, because the probability of heads is 0.5 and 0.5. That's the multiplication rule. Probability of heads tails is heads and then tails, and the key word right there is and we saw that right here with the table. When I'm multiplying things together, I'm saying and. I get heads and then I get tails. And I'm assuming that each coin flip is independent of the previous coin flip. So we can multiply the probabilities right here, and every single one of them, no matter which one we do, would be the same. So all of these are going to have the same probability no matter which one we do. It's all going to be 0.5 times 0.5 because it's probability of getting heads and then getting heads, and they're independent trials of each other. So that is that one. That one is going to be correct. And the next one right here might be a little more complicated. Let's take a look at it. The next one says, what is the probability of the number of girls in a family when a family has 2 children? So we're either going to have a girl or not have a girl. And so when we think about this here, let's draw it with green and black. So we're either going to have girl or not girl. And we're just going to put, here, let's put an X right here. So either, and we'll put a red for it. So either have girl or not girl. And there's the X. So when we have 2 kids, these are the possibilities right here. Girl, could have 2 girls. We could have not a girl, not a girl. And I want you to think about this for a moment here. There we go. Here's all the possibilities that could occur. If you look at the number of girls there are in this family, here's 1. We did them a little out of order here, but you can see it, and I'll vanish out of the way. You can see right here the amount of girls there are, and I think we can probably move this over. Click it all right here. So when you think about this, these are the sample space of everything that could occur. Oh, that's interesting. Somehow clicked really quickly. This is everything that could occur, and there's the probabilities of these. And you can see when we make a table out of this, we can see the probability is more likely what? The probability is more likely that you will have 1 girl. The probability of 1 girl is 50%. And if we look at the probabilities here, it's just depends on how we do the mathematics. But all of these can't be equally likely, no matter how we define the probability of a girl. The mathematics will not be equally likely. And so this is not going to be equally likely for all the events. The more likely thing is 1 girl, the less likely thing is 2 girls, and the other less likely thing is 0 girls. So they are not all equally likely, and these are the set of outcomes we talked about. They are not all equally likely. So here we go with an interesting one. This one's pretty complicated. This is probably the most complicated one on here. Flip a coin until you get a head or 4 consecutive tails. So let's just flip a coin here. You ready? And we'll play this game. So we're going to go to our coin flip. We're going to flip a coin until we get heads or 4 consecutive tails. I stop. I flipped a coin until I got heads or 4 consecutive tails. So that instantaneously means we need to have this in here. So that was one of the things that could occur. So that did occur. That's in the sample space of things that did occur. We flipped a coin until we got heads or 4 consecutive tails, which really narrows it down to 2 possibilities here. You're going to flip until you get heads or you get 4 consecutive tails. So you see here, they got tails, 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 tails. They got the 4 consecutive tails. They stopped. So there it is right there. Now, when you think about this, I got actually an event that was 50% likely because we already know from coin flips. That the probability of getting heads is 50%. So when you think about this one right here, we can list out the sample space right here. And we have heads, tails, heads, tails, tails, heads, tails, 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 heads, tails, 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 tails. And so this one is going to be 50%. And this one's going to be 0.5 to the second because they're multiplying together. So it'll be 0.5 to the third. This one's going to be 0.5 to the fourth. And this one is also 0.5 to the fourth because we're just multiplying here 0.5 times 0.5 times 0.5 times 0.5. Now, if you add these all up, yeah, which one do you want to go over, Ryan? We'll do that one next. What do you want to do in BS 320? Feel free, Ryan. Sorry, I didn't see that chat maybe right away. I don't know how long ago you said it. Go time toggles. Oh, good. It was only a minute ago. Good. I feel bad. Ryan, anything you want to go over? Feel free to say, hey, Brian, can you go over this topic? And we'll go over it. You got it. So what's interesting, if you add up all these probabilities right here, all the probabilities will sum up to 1. If you just add together 50% plus 25% plus 0.125 plus 0.0625 plus 0.0625, you will get 100% because this is the sample space, everything that can occur, and they are not all equally likely. They are not all equally likely. They have different probabilities, lower probabilities. The most likely thing is that you're either going to get heads, and then the rest of it has 50% probability. So you'll either get heads or not heads, and then you'll go down this track of not getting heads. So what is the sample space when you roll 2 dice? So we're going to roll 2 dice and record the smallest number. So let's roll 2 dice right here, and we can actually do this in simulation, which is really cool. Let's go here to dice, and we'll store into a dice 1 through 6. And what we're going to do here is we're going to make a vector where we sample dice, and we sample one number from it, and then we're going to make another element to this vector where we sample the other dice. Here we go with sampling dice. Now I want us to think about when clicking regression, do we ever check this compile in the case? We don't. Here, we'll do that next, Ryan. You got it. Let's talk about doing the check regression, and yeah, and then we can do some interpretations. You got it, definitely. We're going to focus a lot on class on that, but we'll do it here too. You're here, you get to ask the questions. I'll finish this one, and then we're going right into that. So does this make sense? And this is good here, Ryan, because we're kind of doing a little 320, or we're talking about coding. I have a vector created where I'm sampling a dice, and this is the first one I'm sampling, and this is the second one. I did this the long way. I heard Dr. Petrie saying, like, why didn't you just do it that way, Brian? And I was like, okay. There we go right here. So now we're sampling a dice, and we can get the same number twice because we got replace equals true. I'm just letting it maybe, there we go. Now we're going to take the smallest number here. So let's go here and go min of this. Now, what would be a very hard number if we take 2 dice? So Ryan, don't worry, like if you don't know, it's all right. But if we're taking 2 dice and we're going to take the smallest number we roll from the 2 dice, what would be a hard number to get if we take the smallest number? And you notice we get 1, 2, 3, 5. That was interesting to get 5. If we take the smallest number every time, what's going to be a very hard number to get when we roll 2 dice? Oh, we finally did it. I wish it'd show it, but we finally did it. And there's only one way to get that. If you roll 2 dice and you take the smallest number on the 2 dice, as in we roll 2 dice, let's show rolling 2 dice again. We roll 2 dice, I'm going to record 2 right here. So I'm going to roll 2 dice, and I'm going to record 2 exactly. And if it's the largest, what would be a very hard number to get if we're going to record? No way. Wow. Or you're just being, that was a 1 in 36 chance. There's only a 1 in 36 chance you would get 1 because you'd have to roll 1 on both your dice, and we just did it again. It could happen. It's very unlikely to occur. It's only a 1 in 36 chance. You're going to, there it is again. We're just hitting the lottery today. You see, now it's not occurring once I say we're hitting the lottery. You're more likely to get higher numbers here because the only way to get 1 if you're recording the highest number. So it's only a 1 in 36 chance that you roll a 1 and a 1. The more likely outcomes, like how would you record a 6 here if you roll a 6 in anything else? So right here, these are not equally likely outcomes. If we were to go through, this would be a lot to write down. If you were to write down all of these outcomes, you'd have to write down, like, we'll do the min version of it again. If you roll a 6 and a 6, that's going to record a 6. If you roll a 6 and a 5, that's going to record a 5. If you roll a 5 and a 6, that's going to record a 5. If you roll, because we're recording the lowest number now, but we could go to the other side. If you roll a 6 and a 1, that's going to record a 1. If you roll 6 and or 5 and a 1, there's a lot of ways to record a 1, because as long as you have 1, 1 in what you're ever doing, you're going to record a 1. So there's a lot of ways to record 1s, because if you roll a 4 and a 1, a 3 and a 1, a 2 and a 1, a 1 and a 3, a 1 and a 4, there's a lot of ways to record 1s, but there's only one way to record a 6 here if you're recording the lowest number. So that one's a lot to plot out. You'll record the numbers 1 through 6, and they are not all equally likely, and we have done it. There we go. That's a pretty tough one, but I want you to think about the in-depth way we're talking about here with the different sample spaces, with flipping a coin, with the girl, not girl problem, with the flipping a coin till we get heads or tails, depending on the sequence, and with the rolling a dice. And so hopefully we can show simulations right here to help make sense. So Ryan, you were wondering about the conditions right here. When checking a regression, do we ever use the second plot in this class? And could you go over some interpolations? Yep. Let's look at the check regression. And Ella, feel free to ask any questions you want. Ella, ask any questions. Okay, so Ryan, let's do this from the start, the very beginning, a very good place to start. So Ryan, what are you going to do first right here? What are you going to do first? Let's do all the steps right here. What is the first step you're going to do right here? The very first thing you're going to do is what? And what decisions will you make? What decisions will you make? So what's the very first thing you'll do? And I can't really be on the screen now unless I be blocking the output on this. What will be your first choice right here? Puppet Shark, what do you think? We won't do that first. We won't do that first. So the very first step, I wish, I have it in a, let me go grab it. 2 seconds. I'm going to go grab this. Yes, I am doing all of ours. I'm gonna go grab it. I've got a picture of it on here. Here we go. Let me take a picture of this. 2 seconds. And here are the steps for checking the assumptions. I'm gonna bring over this picture right here so we can see it. Okay, here is the steps right here for checking assumptions. And there we go. Awesome. I need to just store this on my computer. Okay. So the very first step is what? So what is the very first step right here? What's the very first thing we're going to do when we check assumptions? When we check assumptions, we're going to do this first to start. Start with this. So go to step 1, and you'll actually do it for each one. You'll go through each one. You'll start with linearity. You are correct about that. We are going to look at linearity, and we're going to do what for linearity? Check the p-values. Yep. So you're going to start here, and you're going to look at this. So what do you think about that p-value? Which these are the same in the simple model. They're the same. There's just the linearity condition. So what does that mean? And you are 100% correct. And so I'll bring up the notes here, but without using the notes, let's see if you can use your notes if you want. But what does that mean? Like, what does that mean for the condition of linearity? What does that mean? What does that mean for the condition of linearity for this model? Yep, and you're right. So we pass right there. So do we, like, what, and like, I should have put stop. I shouldn't have put can stop. We're just going to stop right there. So since we're just going to stop right here. Does that make sense? Condition is met. We are good. Assumption is good. Does that make sense? Like, you don't continue on. You don't need to do anything else. Like, I put can stop, but I should just put like stop. Like, you're good. Stop going on. And so you are right that also on the equal spread, we are good. So when we do equal spread, we look at the p-value and we're good. Now, if you notice this on the normality, what do we have here? So what's the deal? What's the deal with normality? What's the deal with the normality right there? What's the deal with the normality right there, and what's going on with it? It's a good review of conditions right here. Yes, and when it fails. Oh, so you're right there. You're right there. So pause. So once we fail, so you failed. Well, you're on the right track, but go through in the steps. Like, go through. So and I guess I need to move just a tiny bit more over. There we go. Now it can all be seen. Yeah, I have to be over here. So what do you do now? Go through the steps. So what do you do now? So you've got a bad p-value over there. We've got it highlighted. The p-value is below 0.05. Bad. It just means that there's an issue. It means that you reject the null hypothesis that the normality of the residuals is good. The null hypothesis for this is that normality of the residuals is good. We reject that. We have evidence that the normality of residuals is bad, hence the low p-value. Reject the null. So now what do we do right here? Now, since we rejected the null, what do we do next? What do we do after rejecting the null? Yes, exactly. Check to see if the sample size is greater than 25. Is the sample size greater than 25? Is the sample size greater than 25? Yes or no? Is the sample size? So it's on the screen. See if you like it. It really kind of makes it clear. Like it is greater than 25. You're correct. So the sample size is greater than 25. It's right here. Kind of makes it clear. It's like n sample size, all this good stuff right here. And yep. Okay. So now we need to look at the normality of the residuals. The normality of the residuals is going to be this plot. Let's take another screenshot of this and just talk about this plot right here so we can make sure we understand what's going on with this plot right here. So this plot right here, you will have linearity and equal spread. So the linearity is this. I'm going to highlight it to make it clear. This is the linearity. That's your line, and you're asking, does the line slice through the middle of the data? But you don't have to look at it. This one passed, so we actually don't have to do it on this one. Does that make sense? You bet, Ella. Let's do that one next. You got it. And then we'll come back and do interpretations of that so we can jump between 320 to 1. You got it, Ella. So we'll be doing that in about 4 or 5 minutes, probably. The equal spread, I'm going to do like bars around it like this. The equal spread, we look at it like this to ask, is the equal spread? We don't have to do this. This one passed. But the equal spread, you look to see, like, is it equally spread out among this at all times? Now, over here on this one, it's important to note that this is the normality of the residuals. And so, I mean, that is the residuals, and you can view the residuals at all points. But this is going to be your normality right here. So last step, if one fails after checking the sample size, is 2. And so we don't really fail the sample size. It's like, well, so it's like sample size tells us if we can continue. I don't have that picture up anymore. So it's not like really you pass or fail the sample size. A lot of times people think of it that way, but it's like if you don't have a large enough sample size, you just stop and you're like, well, this is a bad model. I shouldn't use it. So if we like you continue on if you have a large enough sample size. If your sample size is too small, it's game over. You're done. No, that's a good way of phrasing it, Ryan. Thank you. 20 points right there. If the sample size is large enough, we can continue on. It's not like large enough, like set to 1 large enough, but it means to be very specific on why we need a larger sample size. If we fail the test with a small sample size, the problems are usually so drastic that the plots would even show it. It's not a bad idea to look at the plots anyways. You could always look at the plots, but when you have a small sample size, the reason you'd fail the test is due to major problems. So it's pretty much just stopping anyone from even using anything. Like if you fail the test with a sample size of 10, your model's bad because the tests they're structured with smaller sample sizes. You're less likely to fail, but with a sample size of 10, your model, you should not use your model because there's good reason to think that your model, it's not going to be a good reflection of reality. This model right here, though, is going to have some problems with normality. And how bad are these problems on a scale of 1 to 10? How bad? 1 means perfect. 10 means, oh my gosh, throw away that model. Worst model I've ever seen in my life. How bad are these problems 1 to 10? I've got a range of answers. How bad are these problems 1 to 10? I'll tell you my range in a moment. I'll see if you fall in the range. For the normality of residuals, how bad are these problems? How bad are these problems for the normality of the residuals? 1 to 10, what do you think? It's all right. You could be way different. I'd give it, my range was 2 to 5. 2 to 5. So don't worry. This is where we kind of like, this one right here just looks like it's got some low outliers on the bottom side. That's where these points down here are connected to these over here. These points over here are connected to these up here, which are also these points down here. All these points are connected. There is ways to look across the plots. We often say like we don't look at the middle plot. So I try to tell people not to look at this middle plot because you don't want to be gauging the normality on that. But I would say, yeah, the outliers could be worse. I could see some stat. I'd love to ask. I'd love Petrie to say like, I wish I could just like send this to Petrie right away and be like, rate this model, like rate the normality of residuals 1 to 10, with 1 being perfect and 10 being horrible. I'd probably give it a 4. Let me give it a 4. I've seen craziness. I've seen. You want to see a really bad QQ plot? Watch this. Watch this. So I have red class loaded up. Really? I do not understand for the life of me why it does this a lot of times. Because watch this. I'm going to close out of this. Don't save. And watch this. I'll reload. Probably have to reload red class now. But I'm going to reload this, and all of a sudden the QQ plot work. We're not going to change anything. I'm probably going to have to reload red class. I do not understand why this does this. When I update, my computer hates me. Wow, my computer really hates me. So here we'll load library red class. And then we'll go QQ plot of random exponential numbers, 1,000 points, and there you go. This one is probably a 9.5 out of 10, just because I always think there could be worse. If you look at this one on the QQ plot, there's strong evidence of non-normality. But even if you have something that is normal, like this data is normal, you will see errors in it. So these are all coming from normally distributed data. I'm trying to make one that looks kind of baddish, that looked more like ours. But these are all normal data because random normal right there at the bottom. Yeah, look at this. Over here at the end of it, it definitely escapes over there. You got to bend over here. This is actually from normal data. So the data behind this is normal. And we do see a problem up here where it's escaping with some outliers. And then there's a little bit of a bend outside here, a little maybe modality to it. Not strong, but when you see those waving throughout, there's some modality. I've looked at too many QQ plots. But this is actually coming from normal data. So this is actual normal data, but normal data can sometimes be a little bit not normal, which is weird to say. Like, how can normal data be not normal? Well, it's just random chance. Okay, so we'll come back. We'll do some interpretations, Ryan. You purchase a 5-pack. We're going to go over here back to 201. Let's go to space for a second. Okay, we're going to get 201 up and going. 201. You purchase. This helps me do those cuts in the videos. So, Ella, you got it. You purchase soda. Or is it soda? 5-pack of new light bulbs. I like these questions. Let's put on some music. Yeah, here we go. Where is it? Here we go. Found it. Found it. Back over to the main screen. Let's do this. You purchase a 5-pack of new light bulbs that were recalled because 22% of the light bulbs do not work. So we see some notation we're going to have to take down immediately in this problem. What is the probability at least one of your light bulbs is defective? So I like to do a lot of drawings for these. Let's bring up a new Word document. 10,000 Word documents, 10,001 Word documents. So you purchase a 5-pack of light bulbs. So let's visualize this here. 5-pack. Why do they sell 5-pack? Here's your 5-pack of light bulbs. Sure, they must be different sizes. I don't know. It's a multi-pack. 5-pack of light bulbs on the screen right now. The probability, let's look at probabilities here. The probability, 22% did not work. So we got broken and working. So probability, really? Probability of broken is 22%. And the probability of working is 78%. So now we got the probability of light bulb is broken. You got it, Nick. He's playing a lurking variable again. Yeah! Let's do lurking variables after this. Wait, can you do 21%? You bet. Let's do 21%. No reason. No reason, right? No reason. 21%, yeah. So if it was 21%, there's the probability of broken. There's the probability of working. You're here. You get to ask the questions. You bet we can switch to 21%. So we want to figure out the probability that at least one of your light bulbs is defective. Now, would you agree with me that either all of our light bulbs will be working? Let's look at this. Oh, it's such a good color for that. Would everyone agree right here that either all of our light bulbs are working or what? I need people to say it in the chat. Either all of our light bulbs are working or what? Either all of our light bulbs are working or what? So either all of them will be working, which they're not right now. Either every light bulb will work or what? Not all the light bulbs will work. So that makes sense right there. Either all the light bulbs will work or at least some of them won't work. At least one will be defective. So what is the probability of every light bulb working here? We can almost do it through the song. We're almost there. What's the probability every light bulb works? We'll do it at the very end of the song here. What's the probability every light bulb works? Well, that's your first light bulb works, your second light bulb works, and your third, and your fourth, and your fifth, and these light bulbs don't care about each other. So the probability that every light bulb works is that. But we're not interested in all the light bulbs working. We're interested in at least one doesn't work, which means not all the light bulbs work. There it is right there. That's the probability of everything but all the light bulbs working. Yep, Ella, this would be, does this make sense here that this is the probability all the light bulbs work? This is the probability everything but all the light bulbs work, which what we're talking about here is the set of all other scenarios. Like there's a huge set of scenarios over here where, you know, if you carry out all the possibilities and had to draw them all out, you would need to draw out like possibilities like work, 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 not work, not work, not work. There's a whole bunch. Did the stream crash? Okay, Nick, we look to be good. Oh, scaring me right there. We look to be good. Are we good? We crashed before. 26 minutes in. It looks like I'm still streaming. Look at the statistics on this. So stream quality good, CPU at 5%. We're going 5 kilobits up. And no one said we're 0 dropped frames. 30 frames per second. It's good. Okay, good. It might have just been, yeah. I don't know. There was like a week where we just had like crazy internet issues and it was kind of around the storms. I don't know if suddenly, good to hear that, Ryan. Good to hear that. Just got here, all good, awesome. I like doing these visualizations like this. I hope people can help visualize it in your mind too, that we either have that all the light bulbs are working, which is the probability of 0.79 to the 5th power, or we have at least one is broken. So either all the light bulbs work or at least one is broken. So the probability of there being at least one defective light bulb. And so we can do ours. Our question was a little bit different on this one. We had 0.78, and we're just going to raise that to the 5th power. 2nd, 3rd, 4th, 5th. Copy, paste. 1 minus, copy over here, drop in. Oh my God, what's going on? Go over here. Okay. 3 decimals, and we're good. Boom, got it. Sure, let's do one more 201. Then we'll hop back over lurking variable next. So lurking variable next. A student figures that he has a 38% chance of being late to class. Cool, let's do this one. Student figures they have 38% chance of being late to class. Let's do that one, then we'll hop back to 320 again. And we'll do another song here. I think these songs help me relax too. It's like, just like, I don't know what, pro or con, just be honest. Like, do you guys like the music in the background when we work these? Like, be like, you can tell me if it's like, whatever. But I like it sometimes. I like, keeps me just like, just relaxed. Not that I'm like hyped, but like, I don't know. A student figures that is a 76% chance. I do too. A student figures that he has a 76% chance of being late to class. Being let out of class late. If he leaves class late, ooh, that sounds to me like that is dependent. If he leaves class late. Oh, sorry, Ella. There is a 66% chance that he will miss the train. What is the probability that he gets out of class late and misses the train? So what we're doing right here is we're going to do what to these probabilities. So we're going to take these probabilities and we're going to multiply them. But what's interesting is we can actually make the set of all events. This one's rather interesting when you carry it out. What was the probabilities again? 76, 66, okay. So the probability of late out of class is 76%. The probability of not late is 24%. Now, if he's let out late, the probability of miss is 66%. And probability of not miss is equal to 34%. So hopefully that makes sense right there on whether they miss. And so it almost seems like we can't multiply them together, but it's actually giving the next probability. We're saying this happens and then this happens. And we know the probability. Now, here's what's interesting about this problem is if he is not late, so he will not miss his train then. So if he's not late out of class, this would be one possibility. I'll put these in green right here. So we'll put not late and he'll make his train then. And the probability of that is 24%. Because just think, he's not going to get out of class late, so he's going to make his train. The probability of not late and... Oh, that's missed train. Probability of not late, not missed train is 24%. Probability of not late, misses train is actually 0%. So it is dependent because he's not going to miss his train if he's not late out of class. Does that make sense? But now, what is the probability that he is late out of class and misses his train? So what is the probability he's late out of class and misses his train? What is the probability he's late out of class and misses his train? What is the probability not late? What is the probability he's late out of class and misses his train? The probability he's late out of class is 76%. The probability he misses his train is 0.66. Sure, and then let's divide by 100. So just so you can see. 76% times 0.66. There it is right there. So, and that's probability late and misses, right? Now, you know what's really interesting right here? This last one is going to have a probability of 0.2584. 0.2584. How'd I figure that out? Do you think Brian solved in his head, because we're doing late and misses not, and late and misses, oh, we got the probabilities reversed right here, don't we? No, late and not miss. Good, we're good. Do you think I solved in my head probability of late and probability of not miss? How'd I figure this out? How did Brian figure that out in his head? What did Brian do in his head? And we can change these from percents over here. What did Brian do in his head? What did Brian do? What did we do? Oh, that's all right, Nick. Oh, I'm sorry to hear that, man. How did Brian figure out that bottom probability? One more song today. One more song. Just chill. How did I figure out this bottom probability right here? Right here. How did I figure out 25.84%? And the answer is because all of these right here are the what of what could occur. These are all the what of what could occur. This is everything that could occur, so this is the sample space. He will either be not late and not miss his train, and if he's not late, he can't miss his train. This is changing the probability here. And yep, you're right, actually. You know what, Ella, you're perfectly right. This right here, the complement of all this is this. And what Ella just said to me is they add up to 1. So that is the complement. Like, I've now drawn these as complements. You either late and not miss your train, or something else occurs. So they add up to 1, and the sample space can be used as complements. So we're reviewing some big topics right here. The answer to this question is just solving for this one right here, and that will get us the probability. We did more advanced stuff with this, but it helps to just kind of review these questions at, like a deeper level sometimes. And what is the probability he gets out of class late and misses his train? Let's make sure we grab the right one. Late and misses train. So round to 3 decimals. Really? Really? Let's double check it. Probability he gets out late. I'm gonna double check my work here. Probability he gets out late. Okay, gets out late and misses the train. Okay. Good. Round to 3 decimals. Woo! Got scared there. Does that make sense? Always talk it out, because you're saying this happens and then this happens. It's if the probability were to change, but it's actually giving you the probability. This one does sound a little bit confusing because you're like, okay, that is dependent. But it's saying that if this happens, then the probability of this is this. So then you can say, okay, what's the probability that this happens and then this happens? Because it's giving you the next probability, saying this will be the probability of this if this first event happens. So, and we list it out. This one is a little bit confusing. It's like, theoretically, it's a little tough to like understand because there are dependent events in here, but it is giving you the probability given he gets out of class late. But there is no probability he would be not late and miss the train. So that would change the probability here. So good stuff right there. It's just that if he gets out of class late, the probability he misses the train can be used then. Like this is almost like a subset within here that if you look at this right here, you've got the subset of possibilities right here that break it apart. This one right here is its own probability by itself that exists without the other probability. Like if he is not late, he will not miss the train. But if he is late, then you've got these sub chances right here. Like given he is late, then the probability he misses is this. Yeah, exactly. And so hopefully that makes more sense right here as I show it like this way, that if he's not late, he can't miss the train. Because apparently the train always comes on time, and he'll always get the train. So what's the probability of not late and miss? 0%, and that's where dependent events come into play. Like you can say like, well, it's going to change the probability because now since he's not late, he won't miss the train. So I hope a little bit more complicated right there, but good stuff. Like we made it way, like I want us to try to understand things at this level, because I could just say, oh, just multiply these two probabilities and then you solve the problem. So like, here we go. Let's look at another version of it. Here's how you solve the problem. You look at this number, you look at that number. So you go 0.49 and then you go 0.53 and there's the answer, round to 3 decimals. So there's the quick, like, here's how to get the answer, but we always want to go for the knowledge on it. So if you understand the knowledge on behind it, you can get the test question right. So don't be like, do I understand what the problem is trying to show me? And the last thing before we talk about lurker variables, this is what the problem is trying to show you. This is like the deeper knowledge behind the problem. Exactly, Ella. And thank you for being here, Ella. Let's throw some 20 points for positivity. I really appreciate it. This is the deeper knowledge I want people to work towards. I mean, I want you to get great grades too, but great with great knowledge comes great grades. So the better your knowledge, the better your grades are. And it's like, don't just solve a problem, understand the why behind the problem. Let's hop back here to 320 and let's look at some models. Let's take a look at some regression models right here. Okay, do we have any models stored in the global? My gosh, what have I done? What model is stored in the global environment right now? Oh my gosh, we got a crazy model right here. Okay, we need a lurking variable model. Classic stuff right here. Let's go classic. So this is... No, I did this example yesterday. I guess we could. Height. No autocomplete. Wait, is it on? Is it what? Okay, it's stored. Okay. When you look at this right here, what does this model tell us? We did an example like this yesterday. I might do it today. It's just a good example. It's a top tier example of a lurking variable. So when you think about this right here, what would this mean right here? What does this mean? I received the same 10 questions on the... Yep. Wait, I received... When I retook the Canvas quiz on to one, so what it is, Kayla, is like that set of questions is basically like a static set. So the goal for it is that people get hundreds on it. And so giving the same like static questions, which then harms the ability to like practice it. Like if it gave different questions, it'd be really great because then you could like cycle through a whole bunch of questions. But those are questions that are actually in the question bank. So it's basically like an example, like short version of the test. Does that make sense? So what you're getting with it is like here's like a short version of what the test could look like. So this is R squared right here, right? And so what does R squared tell us right here? What does R squared tell us? So the reason, Caleb, why we wouldn't, and we can always improve these things. Like I want suggestions and stuff. At least the reason why we wouldn't have it change so much is because it's actually giving you questions. And you're like, well, why don't you just give us, I don't know, you could say, hey, if I practice all the questions and get them down, then I would understand them. Yeah, I don't know. It's like it's tough. So there's some questions you're seeing that will be on the test, and it's like a short, yeah. Sorry, and I think Ryan got it. 33.86% of the variation in height is explained by the variation in number of body piercings. Like people's variation in body piercings explain height, and you can see it over here if you visualize it. Let's visualize it and take a look at this model. And we can see that what do we got going on right here? There is a definite failure of a condition. I'd like to take a bunch of time to see yeah, I know. I think we should make improvements on that, Kayla. Give some advice on that, and I'll be thinking about improvements, especially for the final, that maybe we could have. What I do want is for people to get the hundreds, so that way they can get 100. If we change the questions, it'd be harder to get 100 because you might get different questions, and you might get like an 80, then a 90, then an 80, then a 70, then an 80, then a 90. I mean, I don't think it's too hard to get 100. That is due tonight. Please, please do it. I need to send out reminders after class, after office hours on this. Please do it. It's not too hard to get 100 on. Please do it. It shows you what the test is going to be like. Gets everyone prepared. Please, 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 please do it. So here we'll show, well, we got the announcement up. What is that announcement? Announcement when everything's due. Make sure to do that tonight. I need to look how many people have done it because I'll be emailing people midterm, all intermediate. Gosh, I sent out a lot of announcements. So here it is. A review quiz right here. And there's the info on the review quiz. Make sure to do that by tonight. Way to sample is to describe the population parameters, not the... A sample gives us a statistic, and a statistic is an estimate of a population parameter. A sample gives us a statistic, and the sample gives us an estimate of the population parameter. Yep. So a sample gives us a statistic, which is an estimate of a population parameter. Does anyone see any issues with this model right here? And why do we see such a big grouping right here at 2? Does anyone notice there's a whole bunch of... I kind of see 2... I want to look at this model. I want to just think about it theoretically here for a moment. I see something going on right here. I see something going on right here. What's going on with this? What's the deal with this? And what's the deal with this right here? Look how I'll highlight it. Can anyone tell me, like, what's going on with this? Why do we got this going on? And why do we got this going on? Maybe the total number is large enough, or yeah, I think we could do something like that. It could be, I think that's the changes I'm considering right now, is like if we took like 25% of the total questions and say like, you know, like these questions are 25% of the questions that like you're drawing from 25% of the total test questions. So at most, if you practice this, you would see 25% of the test questions. I think we should definitely go towards that. And I think I could start making those changes because I think that would improve. I think that'd be a really good improvement to it. It says a sample is to have enough data to understand the sample. Let me look at, can you copy paste the exact question, or I'm going to go take a look at it while people consider this. I'm going to go grab that one and take a look at it. Look at the exact phrasing on it. A sample, that sounds false to me because a sample is meant to understand a population. Right now, that sounds false. So I'm going to go find the question because it sounds false. A sample would be used to understand a population parameter, but from a sample, we get a statistic. So it depends on how it's being worded, because from a sample, we would get a statistic. So just depending on how we describe this, let's go to preview. So statistics select a representative sample from a large population that we want to study being using. Is that the question? Let me see. I'll have to paste it in here. The purpose of a sample is to have enough data to accurately oh no, that's going to be false. 100% false. The purpose of a sample is to take the purpose of a sample is to understand what? So we do not want to understand the sample statistic. So the purpose of a sample is to have enough data to adequately describe the sample statistic. So no, we're going to get a sample statistic, but the purpose of a sample is to understand the what. So the understand part, we're always trying to understand what's. Like the purpose of taking a sample is to understand the what, the population, exactly. So that's inferential statistics right there. So great job right there, excellent work. So the purpose of a sample is to get an understanding of the population. Yep. And what do people notice about this right here? We've got a bunch of people with 0 piercings. Always try to make sense of your data. Always be like, what's going on with my data here? It doesn't mean these people have to be anything. It's just I have 0 piercings. It doesn't mean anything. There's tons of people who go against trends in data. But I see a lot of data over here at 2. I see a lot of data over here at 2. See very little individuals who have 10. See a lot of data over here at 0. What's the deal with all this data? This is like real data right here. What's the deal with it? What is the deal with it? And 0 is where the intercept would be. Exactly, Roderick. 0 is going to be where the intercept would be. So we can actually see the intercept is somewhere around 70. And there it is right there, hiding behind there. So the intercept is about at 70. There's the intercept right there. Yeah, we'll do the repaired car ones. You got it next here. We're doing lurking variables, and then we could do some interpretations, and we'll do the repaired car one next. You got it, Ella. And so it doesn't mean these individuals have to be male. These individuals have to be females, but males, I would say, are more likely to have 0 piercings. It's just more likely. It doesn't mean you will have 0 piercings. Females would be more likely. Many women have, exactly. But I've got many guy friends like ears pierced. Know many girls who have not had ears pierced. Doesn't mean anything. It's just trends in the data. So the lurking variable here is actually going to be gender. And what happens? Ooh, it's still significant. You know what's really cool? Watch this. Look at that. Now we've got indicator variables in the model, and we've got indicator regression with categorical variables. Ooh, how are we going to do that? That'll be coming up here in about 2-3 weeks. So you can notice here the gender male is super significant. So you say, where is gender female? Well, gender female is the line that's the not male line. So we've kind of got complements going on here too. But you can see here that number of body piercings was super significant. But what happened to the number of body piercings when we added in gender? And you know what? I wonder if we add in weight, if that would help with this model, like take away from body piercings. No, body piercings is still significant. Let me try this. I know a good way to make body piercings not significant. Let's put in the interaction. Yeah, oh, there's an interaction. The interaction's significant? I did not expect a significant interaction. No, the interaction's not significant. Still significant. Oh my gosh. A lot of interesting stuff going on over here. We're seeing probably, this is actually towards the end of the semester. If you're worried about the coding and the end of the semester, are we using multiple R for this test correctly? Exactly. This test only uses multiple R, which is confusing because you're like, is that not for multiple regression? Multiple R is your R squared here. This is your R squared at all times. Great question right there. This is the multiple R, which is your R squared. And you can see in this model right now, the interaction, which is the difference between the slopes of the line, is not significant, even though it looks kind of significant, but it's not apparently. But we see right here that the p-value for number of body piercings went down, and gender male is super significant. So gender looks to account for way more of the variation. And there's one last thing you could check for this. We're going a little advanced here. What? Don't break my VIF, variance inflation. Yeah. Oh, wow, there's not as much variance inflation. Oh, really? Really? Let's do it this way. Huh. Well, I'll be. There's not as much, yeah, I mean, to a certain degree. There's not extreme variance inflation right here. It's so-so. Yeah, technically by our measures, it's kind of high. Last check. Okay, it's a little high. It's a little high. So I actually did a lot of your end of course material right there, checking variance inflation to see the overlap between variables. This is talk about multiple regression world. For this linear model you're doing right now, you'd use multiple R. Always use multiple R to look at the percent of variation in Y explained by the variation in X. So 52.41% of the variation in someone's height is explained by this model. So this would be the interpretation there. If we remove out this and just do the linear model again, 33.86%, and here's the visual of it. 33.86% of the variation in someone's height is explained by the variation in the number of body piercings. There's a huge problem here with the linearity, though. The linearity is going to be a major problem. I can already see it right here. Let's go ahead and do the check regression on this, and you're just going to see that this has crazy problems with that linearity. There's the problem with the linearity we see, and everything's actually a problem. What condition are you most satisfied with here? What condition are you most happy with here? So even with variables, the multiple R is always your R squared. It's just the percent of variation Y explained by the variation X, and it's always multiple R no matter, that's always the R squared is the multiple R, and the R squared adjusted is, don't worry about that so much for the, like we'll talk more on at the next test. For today, probably just be like, I don't need to worry about adjusted R squared yet. Don't need to worry about it. I have mentioned it in class, but don't worry. What is the only one I would say is, yeah, that's pretty good. So you're like, but Brian, wait a minute. You say, but wait a minute, Brian. But wait a minute, Brian. I swear, Brian. But wait a minute. I see it. I see it. Yes, I see it. I see it. I see it. What do I not see? The equal spread I'm a little worried about. I'll tell you why. The equal spread is going to be that first plot. I'm a little worried about the equal spread. I think the equal spread has some issues. That's number 2 on my list. Yep, normality. So remember, this plot right here is going to be linearity, and the linearity is super bad. The equal spread is also kind of bad. It's going to be this one. Put those in red. And the one I'm not so worried about is going to be normality. And if we look at the normality, we only see a little bit of an issue there, and top's fine. I mean, that's okay. That's not that big of an issue. That's not that crazy. The equal spread, though, if we talk about the equal spread, you're seeing some, like, there we got enough data to make decisions. It's second worst because the linearity is really, really where you're seeing that's not good. That's a deviation. That deviates from the linear model. And it was present in the previous plot too. If we go back to this previous plot, you can see the bend throughout the plot, a little bit of a swoosh action there. And at the latter part of the model, it's completely outside the bounds of it. So we are seeing that over here on this one. And I don't really think the normality of the residuals is that a bigger problem, even though we failed the test. So overall, I wouldn't like using this model. I'm going to not be happy with it. Let's see if the multiple actually comes back with better p-values on those. And ooh, look at those residuals. Ooh, the normalities hurt. Normality took a dive right there. You can't do it on gender, and you can look at the overall. Linearity improved vastly. The linearity of the x is still horrible because that's still the x variable we originally tried. You notice we get two sets of predictions right here. The predicted values are basically like the male predictions and the female predictions right here. And the equal spread actually passes now. Yeah, that's pretty good. Pretty equal spread throughout the model, about equal spread. But these low points down here are causing the issue down here. Now, I know I'm looking at this plot and talking about the normality of the residuals, but that's these points right here. So you can kind of trace between plots and see like, okay, you know, over here on the low end, we have things that deviate from the normality. That's actually those points there, which are actually these points over here. That's the points that are too low. So once again, this is your normality of residual plot. Make sure you're looking at that one to indicate, yeah, and I'd say it's pretty bad right now. That's a 5 or 6 on the bad scale. Pretty bad. I give it like a C minus, D plus. I don't know, maybe a C, somewhere D plus to C. It's not good. I'm not happy. But I mean, how unhappy am I? I don't know. I'm actually probably happier with this one than the last one. We majorly fixed the linearity. So we got the linearity fixed, we got the equal spread fixed, but we hurt the residuals, the normality. So, and I think our R squared increased drastically. Real quick, last thing on this. Previous R squared was 33%. New R squared is 52%. I'll take it. And look at this. Last question, then we're going to do Ella's question right here. Why is Brian, so this is an advanced question, like something we haven't covered yet. Why is Brian happy with that R squared adjusted? Really great test question here. Why is Brian, or I should ask, am I happy with it? But I am very happy with it. I look at that, I'm like, okay, this is good. Why is Brian very happy with that R squared adjusted? Why is Brian very, very happy with that R squared adjusted? Like, yeah, that's awesome. I like that. Why is Brian very happy with that R squared adjusted? I'll give it a second here. Put on some music. Why is Brian very, very happy? So R squared adjusted, just a bit of an advanced topic here. R squared adjusted is R squared adjusted for how many variables are in the model because it isn't much lower than the multiple exactly. It's always going to have a penalty on it. R squared adjusted is always lower. It just mathematically has to be unless R squared is 1. So in all instances, save the one instance. R squared adjusted is always lower, and it's based on like how bad our model is. Like we'll see the mathematics on it, but it's like, yeah, exactly. And so Roderick, 20 points right there, jumping in with that 10%. You can actually calculate, well, like how much worse is too worse? Like how much worse would be really bad? We can take this and multiply it by 90% and say, okay, it needs to be at least this. That's kind of like, at that point, we'd say, ooh, that's a big difference. So it's within 10% lower. So you can times it by 90 to find out it's at least this. So that's a metric that Dr. Seaver would always have us use to be like, is it, like the closer it is, the better. Like if it's so close that you don't even see a difference, that's awesome. But closer it is, the better. And that's really, really close. You can actually do this too. Another way to look at it is to take it right here and find out what percent it is of your original, and it's 99.7%. So it's super close to it. It's right at it. We didn't penalize ourselves much, which means we don't have junk variables in the model, and that's a good thing. It means we did not fill our model with junk variables. That's good right there. Can we do the repaired car questions? You bet. Let's do it. 320-201 showing up today. Hashtag show up. That's what we do here. Repair car question. This is a good one. It's a tricky one. Go away. Okay. I think there's 2 versions of this. Yep. One's harder than the other, and they're both different. Let's take a look and throw those questions out there. We might do some interpretations right after this. If you're here, ask your questions. You got this. Okay, a consumer car agency estimates that over a 1-year period, 18% of cars will need to be repaired once, 7% will need to be repaired twice, and 4% will need to be repaired 3 or more times. Now, they didn't give us everything here. They did not give us everything. Because they did not, how do you know they did not give us everything? Because that doesn't add up to 100%. We got 1874. 1874. So we got the probability a car is repaired 1 time. That's 18. Probability a car is repaired twice. That's 7%. The probability a car is repaired 3 or more times. That is 4%. So what is the probability a car is repaired? I do not understand. 0 times. What is the probability a car is repaired 0 times? Now you guys are awesome. You're all helping each other out. Good memory right there. It's good practice. Good to see you here, Elizabeth. 201 last semester, right? Your points might have changed. I'm sorry. Mubot's awake, right? Oh no, you're this semester. Sometimes I just like my brain just goes. I can't remember. What's the probability a car is repaired 0 times? I've got the number in my head. What is the probability a car is repaired 0 times? Because this will be the set of all possibilities right here. So basically, you're thinking over a 1-year period, you have a car. Your car is either going to need to be repaired 1 time, or 2 times, or 3 or more times. So one of these things must occur. This is the set of all possibilities with your car. Your car will either be repaired 0 times. Exactly, Ella. Great job, 71%. How did we get that? Because these are what of each other, Ella? Like if you say car being repaired 1 or more times is the complement of a car being repaired 0 times. So your car is either repaired 0 times or 1 or more times. So your car is either repaired 0 times or 1 or more times. So these are complements. They must add up to 100%. I was like, yeah. Complements. And so what's the probability that a car will need no repairs? 0.071. What's the probability that a car will need no more than 1 repair? So no more than 1 repair is 0 or 1 repairs. So just so we can show it. Oh, I closed it down, didn't I? I gotta remember to keep it up and just bring up the document because we're at, look at all that. So beautiful. So with this right here, why does my computer hate me? We know why. So no more than 1 time would be these right here. This is the probability a car needs no more, and these are disjoint events, meaning we can add them together. The car, or these probabilities are disjoint events, we can add them together. And so let's go right here, and we have the following. The probability that a car will need some repairs, either your car needs no repairs or it needs some repairs. And let's show that visually, because we always want to do that right here. Either your car needs no repairs or it needs some repairs. So here's the probability your car needs no repairs. And the complement to this is that your car needs some repairs. So either your car needs no repairs or it needs some repairs. So very important right there. We see that these are complements. So 29%, which is these probabilities here. Now this is the easy version of this problem, or the easy type of it. I knew it. I knew I did that. I knew I got something wrong. What did we do wrong? The probability, I was like, this is the easy version. I'm gonna get something wrong. That's our one wrong for today. Yay, we did it. We did it. The probability that a car will need no repairs. So, oh my gosh, I did that right. Let's see. Oh, I grabbed this one. Oh, we did it. So I should have looked at our sheet. Oh, we did it. We got one wrong. I even showed it. I showed it. I solved it. No one saved me. No one said, Brian, stop. Don't do it. Don't do it. Thank you right there. That is true. And so there's the probabilities. I saw this. It's because I thought that was, look too quick. Look at your sheet. Write down the probabilities. Like I even circled it and... we almost had it. Almost had it. Okay, I'm back. Let's do that last question here, then we'll hop back in. Let me turn off the music. I forgot it's still playing in the background. Okay. All right, let's get serious. Serious FaceTime. Here we go. Can we do the one owning the 2 cars? We got this one. This one's the tougher version. We can do it right here. I have a silly question. Can you do a visualization of the output? You bet. Let's do that next here. Something that breaks down what each output explains. Yeah. Definitely. Let's do that, Roderick. You got it. So the probability that neither car will need repairs. Okay, so for this one, we own 2 cars. Now, here's something you have to assume about this question, Ella. You have to assume that one of your cars breaking down, which this might not make sense. One of your cars breaking down would not impact the other car breaking down. So what are we assuming? you have to assume that one of your cars breaking down would do what? Not impact the other car. So what are we assuming right there? So one of your cars breaking down would not impact your other car. What are you assuming right there? What are you assuming by saying one of your cars breaking down would not impact your other car? That they're independent. And since they're independent, you can multiply these events together. We've got the rules right here, the math, the word, the rule. This is from the online class. There's stuff right here with gambling and all the rules right here. So we can see the different rules for probabilities. There's rules right there. Take a screenshot if you like. So all this good stuff. After this, can we practice some interpretations? Yeah, you got it. We're going to do all that right there. Let's do it. We got it. We'll dedicate the last bit of class to doing that. We've done a lot of probability. So the probability that neither car will need repairs. Okay, so let's write down these. 15% 1, 15, 9, 4. Okay, so we need the probabilities right here. 15, 9, 4, right? So probability of 1 is going to be 15%. Probability is 2 is 9%. What am I doing? And then the probability of the last one is 4%. Now, the way they describe this is a bit interesting. And so the probability of 0 repairs, is going to be 72%. Somebody double check my mathematics right here because my math's been off today. So that's 13, I think it's 72. 15 plus 9 plus 4, yeah, it's 72. Sure. There we go. 72, good stuff right there. Now, what's interesting is either our car will need no repairs or our car will need some repairs, and the probability of some repairs is 28%. Does this make sense that either our car needs no repairs or our car needs some repairs? So I've now grouped it into two sets right here. Either the car needs no repairs or the car needs some repairs. Some repairs is defined as one or more repairs. So either the car needs no repairs or the car needs some repairs. So just defining it right there. So now when we think about this, let's look at the questions and see what they ask us about our cars. We've got two cars right here. The probability that neither car will need repairs. So let's put this into words. My first car, what? Did not need repairs. And then I want you to use the words here. I want you to write in the chat or practice. My first car did not need repairs. Then what? Try writing this as a sentence to like solve this. My first car did not need repairs. Then what? Try writing as a sentence. My first car did not need repairs. Then what? My first car did not need repairs. Then what? Because we're going to multiply these. So the question is, both cars did not need repairs. So write it as a sentence first. Probability that neither will need repairs. My first car did not need repairs. And what? My first car did not need repairs. The first car did not need repairs, and the second car did not need repairs. Great job, Ella. 20 points right there. Ella, amazing work. The first car did not need repairs, and the second car did not need repairs. So if the first car did not need repairs, and the second car did not need repairs, it's going to be this right here. So that is what you're writing out, and that is going to be the mathematics for the first car did not need repairs, and the second car did not need repairs. So now we have done this right here. There we go. Just copy straight in. The probability that both will need repairs. So I think we should get this one pretty well. The first car needs repairs and the second car needs repairs. The first car needs repairs and the second car needs repairs. So all we're going to do here is just say our first car needed repairs and our second car needed repairs. So the first car needed repairs and the second car needed repairs. So let's solve this. The first car needed repairs and the second car needed repairs. There we go. Now this last one's the tricky one. Great job right there, Ella. Excellent work. Because when you multiply, you're just saying and. The first car did not need repairs and the second car did not need repairs. The probability that at least one car will need repairs. At least one car will need repairs. Well, there's a scenario here. In these scenarios, either, would you agree with me? With your two cars, we'll do here green is good. So either both your cars don't need repairs, or what? I want you to try to say this right here, or what? Like either both your cars do not need repairs, or what? Either both. I have no idea why it does this. I want to contact Microsoft Word. Either both your cars do not need repairs, which is this, or what? Either both your cars do not need repairs, or what? Or at least one needs repairs, or at least one needs repairs. Either both your cars will not need repairs, or at least one, because there is the case where they both need repairs. Does this make sense here visually to say, like, either both your cars do not need repairs, or at least one of your cars need repairs? Oh, and not that they both need repairs, but at least one, because in this instance, one of your cars needed repairs, in this instance, two. So either 0 of your cars need repairs, or at least one of your cars need repairs. Have we figured out the probability that none of your cars needed repairs? Did we figure out the probability that neither of your cars needed repairs? Do we have the probability here for neither car needs repairs? What do you think we'll do with this? This is the probability that neither of your cars will need repairs, found by multiplying, I think it was 0.72 times 0.72. So, yep. That was neither of your cars need repairs. So what would we do here? So that's neither cars need repair is 0.72 times 0.72. And so what would we do to get, you got it. Oh, no, don't raise it. Don't raise it though. You're so close. You're so close. You're so close. You're just going to do 1 minus this. So this is equal to 0.5148. 0.5148. Because that's the probability for this one. And so the probability for the other one's just going to be 1 minus that. Because this will be the set of everything that can occur. So you're just going to go 1 minus 0.5148. And that's going to be equal to 0.4852. I think so. We'll double check the math. Because one of these things, does that make sense right here, Ella? One of those things must occur. So since this is all the set of everything that can occur, it's going to add up to 1 right there. So, what did I do? 5. Oh, I reversed the number. I had white saved there. That's what's going on with that pen. It's pulling back up white. So it's bringing up the white pen. There we go right there. So that makes sense right there. And so you might have had a slightly different number. So you'd raise it if you originally found only one car, but not. Yes. Yeah. If you're doing multiple cars, you have to raise it. And so there we go. That should do it. Yeah. That's what I like to see. I got worried because I got one wrong. I think the question was, the interpretations were way early on. So I'm going to do the interpretation one, and then Roderick, we can do your question next. You got it. We already did the interpretation of the R squared. Let's do this one. We are predicting people's heights. Who can interpret the RMSE right here? We are predicting people's heights. Who can interpret the RMSE? And this is not a horrible model. You can just round it. Who can interpret the RMSE right here? This is interpreting the RMSE. Put a note here. Try to interpret the RMSE. We are predicting somebody's height. That's key information for this model. Who has a good interpretation? This is a good time to practice. Make sure you can ace the test for 320. Interpret the RMSE, or the residual standard error of this model. RMSE, residual standard error, typical miss the model makes. All that good stuff we should know when we see RMSE. What will be interpreted as? And then we got Roderick's question after we do all the interpretation, right? We'll do good 10 minutes on interpretation. So the residual standard error, which is the RMSE. Yeah, Roderick. Yeah, throw it in there. You got it, Roderick. That's great. Our model on average misses by... You got it. Just put the whole thing in. Let's throw some 20 points again. That's it. That's totally it. You got it. Just make sure to put in the... Oh, you can't see it? Oh, wait. I didn't do the command. There's a button right below me right here. Do you see this? Do you see a scroll wheel? There should be a scroll wheel that can change it to HD. Sometimes it'll downgrade just depending on internet quality and stuff. Hubot, you want to talk about HD here? There we go. If Brian's not currently HD, check the scroll wheel on the bottom right of the screen and increase video quality. So there should be like a circular scroll wheel right down here. If you click that, that you can bring it up to HD quality. So Thank you for mentioning that too, because a lot of people don't know. It's like, well, wait a minute, I guess the stream's not on HD today, but it's just YouTube will do that sometimes. It'll be like, if you're, there you go. Thank you, Roderick. I'm throwing another 20 points. You just tell me something like that, like keep me informed of things, because technically it could be my internet. You never know. Our model average misses by 3.07 inches when predicting someone's height. Perfect. Exactly. And you're always talking about it in context of the problem. You can say like, yeah, we're usually off by about 3 inches when we predict someone's height using this model. Like, it's about how much we're off. Let's see how much we missed Brian by. Let's do this. Let's make a prediction for Brian. So this is a little bit about your homework assignment now. We're going to go here and store a data frame. How much do we predict miss Brian by? So we need to go here to number of body piercings. And number of body piercings equals, here we'll concatenate it and put 0 if we want to do more predictions. We'll go here to gender and concatenate male. I think it should do it. Predict model M, new data equals, there we go. How much do we miss Brian by? We miss Brian by 3.6 inches. Yeah. If you roll multiple dice and you record the largest number, does it start at... So here, wait. Let's roll some dice. You ready? We've got this up on the screen still, I think. You ready? Let's roll dice. We're going to roll dice right here. We'll sample dice right here. And we're going to record the largest number. Record the largest number right here. You're going to record the largest number, right? What number would you record right now? You would record what number? Record the largest number right here. Record the largest number. What number would you record? So when you roll 2 dice and you record the largest number, what number would you record right here? What number would you record with these 2 dice rolled? So there's the 2 dice right there. What number would you record? So you're going to record the largest of the 2 numbers we just rolled. What number would you record? Because you're going to record the largest of the 2 numbers. You would record 4. Nice job. How about... Oh, it's going to be so rare. Oh, we did it. Oh my, that's weird. What number would you record for this one? That is so weird. What number would you record for this one right here? Here's what you rolled. What number would you record right here? You're going to record the largest of the 2 numbers you rolled. And what number would you record for these 2 dice? You just rolled 2 dice. What number would you roll? What number would you record right here? So you're going to record the largest of the 2 numbers. You roll 2 dice. They're both 1. What number do you record? You're going to record the largest. And so what seems more likely to record if you, like in this instance, what do you record right here? Or this instance, what do you record right here? What seems more likely that you'll be recording? So this kind of gives away to the next question. So if you look at this, notice how if you roll a 6, you have to record 6 because that's the largest. So it's more likely you'll record big numbers. The only way to record a 1, which is so crazy, is we actually got it twice right here. If we do it again, we're super unlikely to get it. There we go. We're recording a 3, 6, 3, 4, 4, 5, 6, 6, 4, 5, 5. So you always record the largest. So you're going to get more large numbers here. It's very unlikely you'll get a 1, like 1 in 36 chance, because it's 1 6 times 1 6. So it'd be everyone. Great. Oh, okay. We might have just had a blink. I think we just buffered everybody. I saw it do the thing on the thing. I do not understand. I'm going to switch to OBS. So we should be fine. Hopefully we didn't. Yeah, I saw it. It did the thing on my end where it went bloop, and I saw the chat reappear where it like reconnected. It doesn't show it. Hopefully it's small. Yeah, I don't understand. I'd love it. If we get Elon Musk here, I'm going to ask him about his internet. That's going to be my number one thing. I'm going to say, we don't have good, stable internet here. I want your Starlink. Send me up there and get some good internet. All right, so we've done the R-squared today. Let's just do the R-squared on this one real quick again. So we saw that this model misses when it predicts Brian by a little more than 3 inches. It just misses most people on average by 3 inches. Actual minus predicted. Does everyone understand here that the residual equals the actual minus the predicted? Brian found his residual right here. This is what Brian's residual is. Brian's residual is equal to the actual minus predicted. So my residual just blew it up. My residual is 3.6 right there. So the model misses me by 3.6. I am 3.6 higher than the model. So here's the model. Here's Brian. I am taller than the model predicted me to be because I have a positive residual. So you can see things like residuals when you look at your model. Might have a multiple model in here right now, but points above the line, like this black point right here above the black line, has a positive residual. It's a multiple regression. So let's look at the output a little bit more and do more interpretation. And then we'll head over to Roger's question. Thank you, everyone, so much. Great office hours today. You're in. I'm probably not. I'm not that big of an outlier. You have me interested here to find out how big of an outlier I am. I'd have to find someone in the data set here with my point. We can actually, very briefly, this would tell us if something is an outlier. So we actually have a way of analyzing to figure out the undue influence a point would have on the plot with the leverage. This will be something in multiple regression, talking about leverage right here, talking about studentized, deleted studentized residual. I'm probably somewhere here-ish. I'm probably not that far away. Like I probably don't have that big of a deleted studentized residual. Yeah, because I'm 1. Yeah, I'm probably about here-ish. I'm one of these points maybe. So I'd have to find, I don't know. We'd find out if we did the plot. But yeah, I don't think I'm that far away from the model. And so I'd be mild outlier at best. So like I'm above average, but not like, yeah, I don't know. So what else do we have right here? Let's just do body piercings. Pretend the multiple model doesn't exist. Let's just do body piercings and interpret the coefficient of body piercings. So the model typically misses by about 3.07. Exactly, Kayla. That's a great way of putting it. It's like the model usually misses about by 3. It missed Brian by 3.6, so that's not that big of a miss. And that's, Kayla, 20 points right there. That's the kind of deeper understandings. And don't worry, like I want people to keep on thinking about like, what does it mean to typically miss by this? Well, we usually miss by about this. We missed Brian by 3.6. So yeah, it's about what we'd expect him to be missed by. It's like outside of, yeah, exactly. Roger, you're hitting upon to a great deeper understanding right there. It's like we're kind of within about the typical miss. Brian's about at the typical miss. So yeah, you're not that big of an outlier, Brian. We're missing you by about what the model usually misses by. So not that crazy. Brian's not that, he's estimated about properly. Who knows this though? Who knows this? Be very careful. I'm going to give you a bad interpretation. You ready? For each additional body piercing you get, your height will decrease by 0.2 inches. Someone's going to put that on the test. Just listen to that. Listen to it. It's like, no, that's not how statistics works. 201, we need to change this. I'm sorry, 201. For each, this is a bad interpretation. Do not write this down. I need blinking, like, do not do this. I need to make that this weekend, like whenever I do things you shouldn't do. Bad interpretation time. You ready again? Do not do this. Wave my hands around. Don't do this. For each additional body piercing you get, your height will decrease by 0.2 inches. Here's you when you see your score. How do you actually interpret that? And then I'll put it in the multiple world. It's not that hard to put in the multiple world. You'll say 2 individuals who are otherwise identical. That's all you have to say. They're otherwise identical. 2 individuals who are otherwise identical. And that starts it out. Be careful though, it's not always 2 individuals, but we are talking about people in this instance. So we are talking about 2 otherwise identical individuals. If you don't throw otherwise identical in there, don't worry. There's not multiple on this test. Let's just look at this model right here. If you want, I can fix it. It's just going to change the coefficient. It's not going to change much else. Just the coefficient changes. There you go. Okay. Now it's not multiple. Now it's simple. So how would we interpret this now? This is one of the tougher ones. So how are we interpreting the slope right here? 2 people that differ in their body piercings by 1 piercing are expected to differ in their height by, and then whatever the coefficient is, where higher piercings is expected to be short. 2 individuals that differ by 1 body piercing are expected to differ in their height by, be careful, the coefficient that you have right there, the 5.8. That's gender male. So you just grabbed the wrong coefficient right there, Ryan. On track with it. Yeah, no, Ryan, you're right. Just grab this coefficient. Just grab, yeah. You're fine, Ryan. If you did that, and this was the final, it was a 3-pointer, I might give you 2.5 or 2. I'd probably give you 2.5. You're really close right there. The interpretation where the person who has less piercings is expected to be taller. Yeah, Yeah, I would see. He probably just grabbed the wrong coefficient. If that's a 3-pointer, I'd probably give you 2.5. You just grabbed the wrong coefficient. So like, if you lose a half point, it's like a small error where it's like, like I'll take that. 2.5 out of 3, I'll take it. Yeah. So you just grab the wrong coefficient, and that's where if you lose like a half point, it's like you understood. You just made a little whoops error. Like you even were saying like right after you're like, oh, I grabbed the wrong one. But I need to grab the Randy Savage. Oh yeah. Wonder if I could bet Puppet Shark doing that. It would be that hard to make me do that. This one right here, 2 individuals who differ in their body piercings by 1 are expected to differ in their height by 1.25 inches, where the person with more body piercings is expected to be shorter. Look at the interpretations in the chat to see. We're just changing the coefficient right here. So Kayla, just a future-proofing thing. I always try to future-proof us. The only thing you would change right here, I'm going to just write this. For 2 people that differ in body piercings by 1 piercing who are otherwise identical. That's the only change right there. If you're changing it to multiple, it's just going to say they're otherwise identical. So it's super simple to interpret. This one right here is going to be, this is not on our test. This is indicator regression, but I'm just going to mention it here since it's on the screen. 2 individuals who are otherwise identical, but one person is male and the other person is not male. The individual who is male is expected to be 5.8 inches taller. So this is indicator regression with a categorical variable. More on that later on the semester. 2 individuals who are otherwise identical, but one person is male and the other person is not male. The person who is male is expected to be 5.8 inches taller. And you can see that here with the lines. It's literally the difference between these lines. Like that difference right here is 5.8 inches where they're otherwise identical. They have the same amount of body piercings. So you're saying like both of these people have 0 body piercings, but one person is male and one person is not male. Then we would expect the difference in their height to be this. So it's the literal difference between the lines right there. You can see the 5.8 difference. For the difference in height by inches, I think you got it right there, Ryan. Does that make sense? And then we can do the intercept. We'll do the intercept of this one right here. How would you interpret that intercept? Who's going to get full credit on interpreting that intercept? We'll put on some music right here. I'll put on my favorite song. Nah, it's too intense. This is the chill one. How are we going to interpret that intercept? Do I have any coffee? I got like 1 drop. Coffee's done. I think it was a half a drop. Sad times, coffee's over. No more coffee. Ryan's going to start going crashing from the coffee. It's like, this is AMSR with Brian. Just listen to the music. I don't think ASMR has any sort of like actual benefits. We're interpreting the intercept right here. We're just waiting while interpretations of intercepts come in. When an individual has no body piercings, height is expected to be, yeah, I'd probably accept that. I think, Ryan, let me think about that. When an individual has no body piercings, height is expected to be 7.0128 inches. Yeah. That's what we'd predict for individuals. I'd almost want it to be plural. And so, yes, that's going to be the RMSE. So that's the RMSE right there. That is, on average, our model misses by 3.67 inches. We expect individuals with 0 body. Yeah, those are all correct right there. We expect individuals that's the only, Ryan, I'd give full credit for that. Like if I think over it for like 2 seconds and I'm like, yeah, it's fine. I'd probably just say for individuals with no body piercing, the height we'd predict for them is this or is expected to be. There's a bunch of different ways to do it. Like the intercept's more, like you don't have to be exact. Bad words to use for this would be when individuals have 0 body piercings, they will have a height of 70.01 inches or like you just don't want to use the will word. That's where you're going to lose points. If you say like when an individual has no body piercings, their height will be this. So does that make sense? Let me see. So change it more. No, yours is fine. When an individual has no body piercings, height will be. This is bad. Don't do this. This will lose you points. I'd give 1 point on that. 1 out of 2. It's a major error to say will. Like, because you're saying they will, like, you're saying when, like, just think about what you're saying. You're saying when someone doesn't have body piercings, they will be this tall. No, the model is predicting that they'll be that tall. So expected works right there. Like, I'd give you 1 point. There's things you can do that, like, just make no sense or, like, don't really even go with any sort of interpretation. So I'd be like, that's a major error. So the will word And I've just had students be like, I lost point for one word. And I'm like, it's a definite answer when you say will. You're saying, if you have 0 body piercings, you will be this tall. But you want to say, the model is making this prediction. The model, and we'll look at it visually here. I think we've got this one currently stored. What we're talking about mathematically is, and look, there's basically no one who meets this. Most people are far away from it. On average, people are about 3.7. So the typical miss the model makes. So what would the Bare-Bourne's formula be for interpreting the intercept? Here we can take what you have. Here I'm gonna take maybe. We expect an individual. Here we go. And then I'm gonna use the one Kayla wrote right here. We'll put on. Yeah, we haven't listened to this one in a while. I get into like the swing of things. See, this one's nice. I hope this one. Oh, you have to tell us. This one should cause no panic. This one's just nice and relaxing. Would it be better to say individuals instead of individual? Yeah, probably. We expect, but it all matters about the context. Because what are we talking about? Are we talking about individuals? There's a sheet on Discord. Oh, Kayla, you guys are awesome. Thank you for everyone for posting this. I support Discord. I support GroupMe. You guys know I'm in the Discord. I'm always hopping around. I've got 3 messages on Discord, and now you can see it here on my toolbar. Sometimes you'll look down, it'll be like 9+, and you're like, ah. But keep messaging me. Keep asking questions. Keep helping each other out. That's how we learn. We expect. You'd be like, Brian, this is not the same one you wrote yesterday. I know, but there's changes. We expect, and then you have to give it the context here. With, I forgot. I know R does that. So we'll do another one right here. That's nice. That's the best part of the song. We expect context, which you have to get the context for this. Oh yeah, well they'll direct you. We'll help you with Discord. I think maybe Kayla, you said you'd never used Discord and you got used to it, and you're like, hey, it's starting to make sense. We expect blank with x of 0 to be b0. So let's do a totally different one. Let's do something crazier that we haven't done. Let's do football teams. We've got a football team data set. Is it EX3 NFL? Okay. So we're going to make a model here. And I'm going to buy a keyboard and play this song. It's just nice. Yeah. That's... Is there not a wins last year in the... I haven't used this data set enough lately. Big data set. I swear there's wins last year. Next year's wins. There we go. That'll work, actually. I'm cheating to make it work. Y tilde x comma data equals y tilde x comma data equals. We'll do it properly. Okay, so we no longer have 2 individuals. What do we got here? We got football teams. We no longer have 2 individuals. We have football teams. I know, it's so great, isn't it, Kayla? It's under the general chat posted as awesome. It's in Thank you so much, Kayla, right there. I think when you tag people, once you learn your way around Discord, it's really helpful. It's good. It's a really good platform to meet and talk. So what do we got right here? Ooh, I like this. That's a good number right there again too. We'll interpret this model fully, then we'll head off here. And I think, do we answer? I think Roderick had a question. Roderick, if you want to re-ask your question, could, would, and maybe our friends not will. I like that, Roderick. So we've got a, sorry, I missed that comment right there. What do we got right here? Okay, you got, you know what? In honor of Kayla getting to the next tier right here, let's just make it happen so we can all see the next tier. And you can be like, I was here. I'm going to show you guys what you're also here for today. Big announcement. As people are doing this right here, as you are interpreting any of these values on the screen for practice, you can say, I was here. I was here the day when Statua 1 got to... Oh, no! Oh, my gosh. We are 200 views away from 1 million. We are 200 views away from 1 million views. We're almost to 1 million views. Channel have been viewed 1 million times. 1 million. We're almost there. Almost there. Let's get there, everyone. 200 more views and we'll be at 1 million views. What are the interpretations right here? Is it the Vol for Life tier? Great job. Congratulations, Kayla. You made from Brian tier to Vol for Life tier. We'll hit it. We'll probably hit it today. It updates like randomly. So I thought we were there. It'll be 1 million. I'll make a video for tomorrow, maybe. Maybe we'll do the Elon Musk thing in honor of 1 million views. Elon Musk up here on their channel. So what do we have right here? Any interpretations? Any interpretations? Who can interpret any of these values on the screen? I'll see which one you're interpreting. We're ending off office hours here. What are some interpretations? What are some interpretations on the screen? Just try to interpret the intercept, the slope, the residual standard error, which is the RMSE, the multiple R squared, which is your R squared. Those are the ones. Boom, 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 boom. Here's your uncertainty in the intercept. Here's your uncertainty in the slope. Here's your uncertainty in the residuals. Here's your standardized value of the intercept. So we can calculate that like that. There's that value. Once again, this value right here is going to be calculated via this right here. That's going to be there. There you go. Just more decimals are carried out when you do that. But that's just calculating those by hand. We don't need to do that. We expect a football team with 0 wins this year to have... Yep, I'll take expect. Great job, Ryan. Yep. We would expect football teams that have 0 wins this year to have 5.6 wins next year, which is interesting because maybe they get a good draft pick or something like that. So that's a good interpretation that on average, we would expect football teams that get 0 wins this year to get about 5.6 wins next year. It's weird. You say, well, how can you get 5.6 wins? Well, it's on average. It's like on average for these football teams. The football teams that got 0 wins this year are expected on average to get that many wins next year. So what else we got? Any other interpretations? I will tell you how your interpretation is. I will critique it. I'll act like it. I will see how it goes. Oh, wrong button, wrong button. What other interpretations are there? There's the intercept over here where we see 5.6 for the teams that have 0, and there was only one team. Maybe it was that Detroit Lions or someone? What other interpretations? Good to see you, Miranda. We'll go through a few more of these interpretations and we'll head off here. It's Haslam Friday. Haslam Friday. Gotta celebrate Haslam Friday. Feel free if you want. I will also interpret any of these if you want. If you want, we already interpreted the intercept. If you say, Brian, can you interpret one of these values? I will interpret one of these values for you. Say, hey, Brian, please interpret that value. I do not know how to interpret it. I say, okay. All you have to do is ask, and I will interpret a value on here. Happy Thursday, Miranda. Thank you so much for swinging by. Kayla just made it to Vol for Life tier. What interpretations do we need? We've only done the intercept. So what interpretations are there? Let's see. And thank you so much, Ella, for swinging by here. Our model on average misses by... Yeah, perfect, Ryan. That's exactly it. Ryan, you're acing. Man, I'm throwing 20 points out here. You guys know I like when we all learn points. Ryan, that's exactly right. Great practice, Ryan. And when you say that, does that make sense to you? Like, that's like, just when you say it, just be like, does that make sense that I'm saying my model, when I make predictions for next year's wins, typically misses by about 3 wins? Like, that's about how much I'm usually off. Here, let's go to... I don't know. That sounds weird. That's too inspirational. Yeah, no model is perfect. All models are wrong, but some are useful. We got some, like, thinking music going on right now. Oh, you're welcome, Ella. Anytime. Just drop in. Like, as the bass drops. Just drop in and ask any questions you want. Just be like, hey, Brian, stuck on this problem. Swing by. We'll work on it. That's what we're doing with 320 right now, just doing these interpretations. So we see here this interpretation, as Ryan put it. On average, our model misses about... On average, when our model predicts next year's wins, it misses by about 3. So you could say using this year's wins, making predictions for next year, we usually miss by about 3. There's a few ways to put it, but it's the typical miss the model makes when it's predicting wins. And you can see it's about 3. It's about how far the model is usually off. It's the typical size of the residual in the model. The root mean squared error. What do we got right here? We got the wins. So here's bad interpretation. Don't do this. Don't do this. So where can we find previous lecture streams? They're in your class. So make sure to go to the, just before we mention that. So go to the class, and in your class, you will see a button. Every class has a button. And so if you're in like 201, go over here and go to watch class live. If you're in like 320, go over here to watch class live. This will take you to the playlist. So the asynchronous has both playlists for both class, and just you can see a lot of the classes have the watch class live, and that'll take you to the playlist. I guess it's kind of a confusing thing, like watch class live, but got that. The biggest thing is the context. We definitely tried to make that clear on the test. You're welcome, Miranda, anytime. So the context here is 2 football teams. You know, like 2 football teams that differ in their wins by 1 are expected to differ in their wins next year, because that's what we're predicting. 2 football teams that differ in their wins this year by 1 are expected to differ in their wins next year by 0.3. Where the team that has more wins this year is expected to have more wins next year. And if you look over here at the plot, that makes sense. The teams that get more wins this year are expected to get more wins next year. And just 2 teams that differ by 1 win this year are expected to differ in their wins next year by 0.3, where the team that has more wins this year is expected to get more wins next year. So be very careful. Do not interpret this multiple R squared. I do see this commonly. Yeah, it's 2 different teams. Yeah, 2 teams that differ in their wins this year are expected to differ in their wins next year by 0.3, where the team that has more wins this year is expected to have more wins next year. Sometimes people say to me, Brian, this is a weak correlation. Well, you can get correlation from this if you do square root it. So the value of correlation on this is 0.3, which is moderate weak, but we're not interpreting the correlation right here, which is the square root of R squared. We're interpreting the R squared, which is 8.522% of the variation in next year's wins is explained by the variation in this year's wins. Think of it as subject 2 days, 2 teams. Exactly. 2 avocados. Kayla, you got it down. I like that song. I don't really play that one more often. That's a good like energy song. You know, it's better energy. We'll go over here. Nah, it's too much energy. We'll go to more chill stuff. Test opens at midnight. I need to send out reminders to do the practice test. Please do the practice test. It counts for a grade. Please do the practice test. It counts for a grade. I think we've done them all. Yeah, Kayla, you are. We have people tutor for this class. We usually wait till someone's done the class, but I mean, I wanted to start saying, hey, I'll tutor these times and do group tutoring. And if I was in this class and I needed help, I would have you seen the avocado tacos? Oh my gosh, that sounds awesome. Yeah, Kayla, you're an all-star right now. I mean, I want everyone to know they're doing great, but I mean, you won the Kahoot. You could, I got a meeting, everyone. I gotta go. I just literally got the thing for the meeting. Oh no, Brian forgot about a meeting. Okay, everybody, I'm heading off here. I had a meeting, I forgot. I have a meeting right at 3:30. Bye for now, everyone. Bye. I forgot about a meeting. Just got a text on my phone. Bye.